Hello everyone, welcome to GK Math. So this time we are going to solve differential equations by separation of variables. But before we go to that, we need to define some terms. The first one is, what is a differential equation? It is an equation that contains a derivative, an equation that has a derivative of y with respect to x. Now, the next term is initial value or condition. It is the value of a differential equation at a particular point. So, meaning x value and y value are given. Then the next term is, what is the solution of a differential equation? Because whenever there is an equation, what we need to do is to solve it, right? And what is the solution? The solution is a function that satisfies the equation. It is not just merely an x value or a value for y, but it is a function. The solution of a differential equation is a function. So usually we call this general solution. The next is a particular solution. What is a particular? How does it differ from a general solution? Particular solution is a solution to a differential equation when the initial condition or initial value is accounted for. So meaning when we input the given value of x and the given value of y, then that means we are capable to get the particular solution to the differential equation. Now let's take a look at some examples. This one is a force. We notice that force is equal to mass times the acceleration, but we know that acceleration can be expressed as the derivative of velocity with respect to time. So that means this equation is an example of a differential equation. Furthermore, we know that acceleration is also the second derivative of displacement with respect to time. So here S is the displacement function. Okay, so another example is dy dx is equal to sine x. So this is what we usually solve. So when we integrate this, we are actually getting a value of y. So dy dx is equal to sine x. We integrate both sides and then we will be getting y is equal to cosine x plus c. Okay, so y is equal to cosine x plus c. It is a function, therefore it is a general solution to this differential equation. Okay, next example is dy dx is equal to x times 1 plus y times e to the power of x. Okay, so that means this is also a differential equation, but this time it's not only containing a variable x but also y. So this is dy dx is equal to a function of x and y. Alright, so what is separation of variables? A differential equation dy dx is equal to a function of x and y is separable if f can be expressed as a product of a function in x and function in y. So this function in x and y, if we can express this as a product of a function in x and a function in y, just like this, so the f becomes g of x multiplied to h of y. So g of x times h of y, if we can do it, then we can use this technique. Therefore, the variables can be separated to give dy over h of y is equal to g of x times dx. Alright, so that means we have already separated the variables. And after doing that, after separating the variables, what we can do is we can integrate both sides. Okay, because that's going to be possible now, integrating a function in terms of y with respect to y. And the other side is integrating a function in x with respect to x. Now let's have our first example. So solve a dy dx is equal to x times 1 plus y times e to the power of x. Now as we can see, you notice that this right side is already expressed as a product of a function in x and a function in y. So what we can do now is we separate the variables. When we say separating the variables, the x must be separated from the y. So how can we do that? So we can divide both sides by 1 plus y. So the result is going to be dy over 1 plus y. And then the dx here is we can put it to the other side. So by multiplying the whole equation by dx. So that means this is now going to be equal to dy over 1 plus y is equal to x times e to the power of x dx. So after separating the variables, what we can do now is we can integrate both sides. All right. So this is now possible. So you apply your integration technique. So the integral of dy over 1 plus y is going to be equal to ln of 1 plus y. Now what about the other side? So the integral of x times ex with respect to x, what we can do is we apply integration by parts. So it is going to be x e to the power of x minus the integral of e to the power of x dx. Now just in case you forgot integration by parts, you can refer to the other videos that I have, because I actually talk about integration by parts in my um, in one of the videos that I did. Okay, so this is now going to be equal to x e to the power of x minus e to the power of x plus k. Okay, now of course this is a constant. We can actually use any variable to represent the constant. Okay, so this is now going to be, the left side is ln of 1 plus y is equal to x e to the power of x minus e to the x plus k. So again, the general solution of the differential equation must be y is equal to a certain expression. So y is a function of x. That is going to be our solution to our differential equation. So which means we need to express this in terms of y. All right, so how do we do that? The next thing to do is we are going to eliminate this by expressing this as an exponential. So 1 plus y is equal to e to the power of x ex minus e to the power of x plus k. So notice that okay, we can separate this, and the result is going to be e to the power of x times e to the power of x minus e to the x times e to the power of k, because e to the power of k is actually a constant. So what we can do is uh, we can let some a to be equal to e to the power of k to make it look simpler. So 1 here can be transposed to the other side, therefore the result is y is equal to, this one becomes a, so therefore this is a times e to the power of x, e to the power of x minus e to the power of x. So that is our general solution. Now let's have our second example. Solve the differential equation 1 plus x squared dy dx is equal to 1 plus y squared, for which y satisfies the initial condition y of 0 is equal to 2. So here we are looking for the particular solution of this differential equation. So whenever initial condition is given, so that means we will be able to find the particular solution. When you say particular solution, there is no C or whatever K that represents the constant. Okay, so now looking at this notation, it only means that y is equal to 2 when x is equal to 0. So this is the point that satisfies this differential equation. Now let's focus ourselves here. Okay, we can definitely separate the variables, and what will happen is it becomes dy over 1 plus y squared. So the left side contains the y variable. That is what we meant by separating the variables. So the left side contains the y, and then the right side contains the x variable. Okay, so after doing that, the next thing to do is we can integrate both sides, and then apply now your integration technique, your knowledge about it. So the left side is going to be arctangent of y, and then the right side is equal to arctangent of x plus c. Now, to make it less confusing, we don't need to write plus c here anymore, because the c here actually represents the constant anyway. All right, so what is the next thing to do here? Okay, so we can actually get the tangent of both sides, and what will happen, it becomes like this. All right, because you know why? Because tangent of arctangent y is actually equal to y, so it becomes y equals tangent of arctangent of x plus c. Now this is the time wherein we can now input our initial value. So y is equal to 2, and then our x is equal to 0, so it becomes like that. And then we can now get the value of arctangent of 0, which is just actually equal to 0. So this will result to 2 is equal to tangent of c, and we can now get the c, which is equal to c equals arctangent of 2. So now after obtaining the value of c, we can now go back to this equation. So y is equal to tangent of arctangent of x plus c, which is arctangent of 2. Now take a look at this one. So what do you notice? This is tangent of a plus b, wherein a and b are angles. Okay, so we can now apply or use the formula, the compound angle identity for tangent. So tangent a plus b is equal to, if you can still recall, it is equal to tangent A plus tangent B all over 1 minus tangent A times tangent B. So by doing that, we will now have something like this. So tangent of arctangent x plus tangent of arctangent 2 all over 1 minus the product of tangent of arctangent x and tangent of arctangent 2. Now we can further simplify this, because this is just going to be equal to x. This one is just equal to 2. So therefore, it will now be x plus 2 all over 1 minus x times 2, or just 2x. So x plus 2 over 1 minus 2x. So now our particular solution to this differential equation is y equals x plus 2 all over 1 minus 2x. Alright, so I hope that you learned something from today's lesson. So see you next time. Thank you very much.